Saxon Algebra 1, Lesson 40. We're going to have a rave, an exponent rave. We're just going to review what we know, and we're going to push off in some bold new decisions, and we're just going to enjoy every aspect of exponents and their delightful joy in our mathematical experiences. Okay, we know that the simplest version of an exponent is something like this, right? Where there's a letter or a number, and it's got a little floaty number up here. These things have names. This is called the base. It's the full-size number or letter that the exponent is attached to. This little dude up here is called the exponent, or it's sometimes called the power. Okay, later on we're going to learn a new third name for that. And what it tells us is how many times this base is being multiplied against itself. So in this example, x to the fifth, it represents a shorthand way of saying x times x times x times x times x. The 5 represents how many x's are being multiplied together. All right? Now, we have some cool rules and definitions and things that we've learned, right? And I'm going to remind you of some of them. One thing that we know is that you can write a number as being x to the 1 with the 1, or you can take it off and just write the plain base if you want. Any base that doesn't have an exponent can be given an exponent of 1. If you have an exponent of 0, that's a whole different thing. An exponent of 0 basically, this is dramatic, but I'm going to go out and say it. The 0 kills the x and turns it into an angel 1. The 0 exponent just wipes it right out and turns it into a 1. X to the first power leaves it alone, unharmed, but an x to the 0 power wipes it away and only its heavenly spirit remains. Okay, and we call these definitions because it doesn't necessarily have to make sense to us. It's just a rule that we've all agreed upon, and it's just what it is. Now, negative exponents are the same thing. They're just kind of a defined thing. If we have a minus sign up here, it behaves differently. It's a trapeze, and what it does is it flips the base and the exponent down into the bottom, assuming that they're starting in the top, right? It's a trapeze. It flips them down and it burns off in the flip, so it's gone, but the base and the exponent itself stay exactly the same. Likewise, if we've got a negative exponent in the basement, then that is also a trapeze, but it flips it up. So this would become x to the n, right? It flips it up. The base and the exponent stay the same. It's just the minus sign that gets burned off in the trapeze flip. Okay, this is true as long as n does not equal 0, okay? I mean, if we have 0 exponents on things, it changes everything, but it's okay. So that's just kind of like one of those little spoilers, one of those little caveats John puts on things. All right, there's one more thing that we know, and that's something that is called the product rule. And this looks like this. If you're multiplying two bases, right? We're using x as a base, and they each have exponents, then we can simplify that by adding together the exponents. Let me say that again. If you're multiplying the bases, you can add the exponents. Good to know, right? We're going to use that forever. Now we're going to add, there are actually 3 of these special rules that we're talking about. The second one is called the quotient rule, and that's what's new for us today. And it's similar to this, but in this case, instead of multiplying the two bases, we're saying, what happens if you're dividing them? The bases match. That's key to these. I chose x for a reason. The bases have to match. But if you are dividing two matching bases, then you can simplify that by subtracting It's top minus bottom, right? M minus N, top minus bottom. This is a new rule for exponents that we are going to practice using in this exponent rave that we have. All of this is a giant puffy cloud of knowledge, and I want to make sure that you get all of this copied inside the cover or wherever it is that you keep your formulas and fabulous mathematical factoids, because that's all super duper important. And like I said, we're going to be using it for many days to come, many weeks, many months, many textbooks to come. All right, we have a total of 8 problems in this lesson. Don't worry, they're short problems, but we're going to practice using all of this information in these fun little algebraic riddles. Example 40.1. Simplify. X over 6, x to the 6th over x to the 4th. Oh, well, we just talked about this, didn't we? We said that this thing is called the quotient rule, right? And if you've got matching bases that are in a fraction, you can simplify them by subtracting top minus bottom. So this can be rewritten as 6 minus 4, which equals x squared. Yay, final answer. That's correct. Let's do another one. This time, John's giving us the same problem. Oops, I'm sorry, made the 4 too big. In this one, he told us to write the answer in the numerator. That's what we did. That came naturally. So now he's telling us to write the answer in the denominator. All right, well, this part is all the same, right? But somehow we have to take this and we have to write it so it's in the denominator. Now, here's a helpful tidbit for that. Remember this? X to the n, if we want to flip it down, wait, I put that in the wrong place. We can flip it down and give it a minus sign. So we can rewrite this as 1 over x to the minus 2. What the heck? Isn't that crazy? I'm going to give this a little trapezoid home to live in. Isn't that weird? We can take a base with an exponent that's in the numerator and we can flip it down to the denominator by giving it a trapeze, right? And if we wanted to simplify this, we'd say, oh no, now we have to flip it back up, which is what we would want because that's the right answer. These little trapezes can be quite tricky, but also useful. 40.3. This time, John's going to give us a slight variation on this same problem that we've been doing. X to the 6 over x to the minus 4. Now, we don't need to use our trapeze rules on this. We can just go straight to our quotient rule. So this will equal x to the 6 minus 4, right? Because there's a minus in the formula right here. Let me make these separate so you don't get them confused. This is our quotient rule. We're dividing the bases, m minus n. We subtract top exponent minus bottom. So here we have top exponent minus bottom, but we see 2 negatives make a positive, so our final answer is x to the 10th. Oh. Interesting, right? That's maybe not what you expected, but that works. Example 40.4. We're flying through these, aren't we? Okay. This one is kind of, wait. Oh, I'm looking at the same problem over again, wondering, wait, why is that so familiar? Simplify. X to the minus a over x to the b. Okay, now John did not tell us whether he wants us to put the answers in the numerator or the denominator. We can do it either way. So let's first bring the b up to the top, and we'll have them all written in the numerator. So that would be x to the minus a, and then we would subtract the bottom, right? Because that's how we combine them. That is one form of the answer. But the other thing we could do, working from the problem again, I could work from the answer, but I don't want to do that. Let's work from the problem again. We could say, we want the answer in the denominator, so let's take this and use the trapeze to flip it down. Then we would have 1 over x to the a times x to the b, and then we could simplify that. I'll work this way. We could use our product rule to combine those, and it would be 1 over x to the a plus b, right? Because we can add those together. That's our product rule. So this is the other answer that would work. And what's kind of fun is that we can see, oh yeah, that's two forms of the same thing, right? Because if we let these be trapezes and swing them both down, then we would have a plus b. The minus signs would go away. What? This almost kind of makes sense, but it's interesting because the rules all fit together so nicely that we sometimes feel like we're spinning in circles a little bit, which is never a good feeling. But we're going to use this a ton, so you'll get used to it even more. Okay, now we're going to go a little bit further in this wild, happy-go-lucky extravaganza we're having with our exponential buds. We're going to do some distributive property. With exponents. All right, so you know how to distribute. That's the same technique we're using. We just have big, crazy, messy chunks of numbers to multiply together. 40.6, ready? Copying these down can be a little rough. Now sometimes John gives us a floaty term. I am not going to copy it as a floaty. I'm going to push it into the numerator, and I'm going to give it a 1. No floaties. But I'm not changing anything else. There's a lot of minus exponents, but I'm just going to let them ride, and you'll see why in a minute. Okay, I'll let you finish copying. I'll double check to make sure it's right. Okay, so we know we need to distribute, we know that when there's denominators, we just distribute them as well. Now, some students would say, what about these negative exponents? Why don't we clean those all up first? You could, and it would be right, but you know me, I'm always gonna take, I don't wanna say lazy, I don't wanna say it's the easy way out, but you know, simple is better. So I'm not gonna go to the trouble to straighten out the negative exponents first. I'm just gonna ride these through. I'm gonna do all the multiplications, see what sorts itself out, and then we will come up with an answer. Oh, I skipped a problem, didn't I? Yeah, I did. I skipped 40.5. Oh, I was so excited to move on to this distributive property. All right, we'll come back and do that one last. It's really super useful and interesting, so I want to do it. All right, so what we're doing now is we're multiplying this by this. That means if the bases match, we can add the exponents. So here we go. The 4 is by itself. X and x, so I can add them, and that would be minus 2 plus 2. That means we have x to the 0 power, which means it turns into a 1, which means goodbye. And then we have y to the 4th. All right, that's all for the first term. Now we'll do the second term. I'll copy that subtraction sign. 3 times 4 is 12. X to the minus 2, x to the 4th, I add them, and so it's just x squared. All right, now let's do the bottom. This is just y to the 4th, and this would be y to the fourth times y to the minus 2. So we add those, and we would get y squared. Okay, and that means, let's see, over here we've got y above and y below. We know that we subtract when we're dividing, so this would be y to the 4 minus 4, which is y to the 0 again, so that means those cancel out. And that also makes sense because we know that in a fraction, if you have anything on the top and bottom that's being multiplied and not added, you can cancel. So that's another way to look at this, is we're canceling those. So our final answer, is 4 minus 12x squared over y squared. And look what I did. I created a floaty number in my answer, and I feel really guilty about it. But you know what? That's the right answer. Okay, I could have put it 4 over 1, but I don't mind a little float in my answer. That looks cute. Okay, example 40.7. We'll finish them, and then we'll go back and do number 5. Use distributive property to expand. Now, this time John says, write all the answers in the numerator. I want to go back and show you 40.5 now because it's going to help us learn how to do that. 40.5, simplify. There's no distributing in this one. Okay, we have x, y, z. We have it above and below. We know that if we're multiplying matching bases, we can add the exponents. We know that if we're dividing matching bases, we can subtract the exponents. Product rule, quotient rule. So let's look at the x's first. That's a positive 1, right? There's nothing there, so we can add the positive 1. So the x, we used to write this out, but now I'm just going to do it in my head. Minus 5 plus 1 gives me minus 4 in the numerator. Let's look at the y's. 6 minus 2 would be y to the 4th. And z's, this is a 1. So 1 minus 3 is going to be 1 plus 3, so it's going to be z to the 4th. Okay, now this is our answer. However, there's lots of different ways that we can write this. What we have written here is the first one of 4 ways. So I'm going to copy this again. X to the minus 4th, y to the 4th, z to the 4th. This is all bases, or you can say all variables in the numerator. There is no denominator in this expression, right? We shoved it all up into the numerator. That is absolutely fine. Another way we can write this is we can use trapezes to flip them all downstairs. Just a second, I think I did something wrong here. Yes, this is minus 5 minus 1. This should be minus 6, not minus 4. My bad. Okay. It might have helped me if I had written this out. Minus 5 minus 1 would have showed me my answer was minus 6. You know how we did this? Sometimes we would write down the base and then we would write the 6 minus 2. We would do the exponent work here, and then z would be 1 minus 3. And that would be 4. And this would be x to the minus 6, y to the fourth, z to the fourth, all right? So this is a better way to show your work rather than trying to do it in your head because you make silly mistakes and screw it up. And then you have to catch it. Okay, so we can write all the bases or variables in the numerator. Another option is to write all the variables in the denominator. And we use trapezes to swing it down. So what we're going to do is if we want all these guys to be in the bottom, then we have to add a trapeze in. So this would become x to the positive 6, y to the minus 4, z to the minus 4. Right? We would add the trapeze to flip it down. Another option would be to say, let's write all exponents as positive. So I'm going to go back to my original expression here. We want them all to be positive, so that means y to the fourth and z to the fourth can stay in the numerator, but x is going to jump down, so he can be positive too. And the last option is to write it as all exponents as negatives. And again, we'll go back to our original expression here, and we'll say, okay, that one's already negative, so he gets to stay. And then the two guys here need to go down and become negatives. Y to the minus fourth, z to the minus 4. So what you're seeing is that we can do a lot of stylistic changing things around to write these answers however, I mean, really what it boils down to is however John wants us to. To us, we don't really care, right? I don't care. I mean, I guess this one's not the easiest, but it's not that big of a deal to change them, right? So this is a really helpful problem because it shows us these 4 ways to write them. Now, in the problems that we were doing that have distributive property, we're going to go back and then we're going to read and notice that John has instructions in every single one of these problems telling us how he wants the answer to look. So we'll use this as a guide. I want to make one point about this one. Very often John will say, put all variables in the denominator. If you have a number other than 1, like say there's a 3 or a 5 in the front, very often he prefers for that to stay up on top and just the variables go to the denominator rather. Okay, so pay close attention to that, and I'll help you if I see one to remind you. All right, so we're going back now to this problem, 40.7, and John says use the distributive property, write the answer with all variables in the numerator. Okay, and this one he wanted us to write all the exponents positive. Okay, well that looks good. All of those exponents are positive, so we just lucked into that one, didn't we? 40.7 looks like this. Okay, let me double check. This is floaty. I kind of shoved it up because you know I hate to commit to floaty. I want that to be there. All right. I'd like to put a 1 on that y so that I don't make any silly mistakes. And then I'm going to write my whoop-de-doops so I'll remember to do every step. Now I'll start multiplying. Remember that if the bases match, we can add the exponents. So the first one will be x to the minus 2, y to the 1 plus 4 is 5. And then the second one, after the minus sign, will be, let's see, x to the positive 2, and then just the plain y. Okay, now we'll create denominators for them. 1 times x squared over 1 times y squared. Beautiful. Now we can cancel top and bottom. See how things come out for us. Minus 2 just a second. feel like I copied something wrong. Checking. No, that's right. Okay, so this is going to be -2, and then we subtract the bottom number. So when we combine them, we get x to the -4, right? It'll be -2 minus another 2. That's x to the -4 rather. Sorry, I can't talk. And then y to the 5th. And then how can we substitute or simplify this one? X squared, and then we have 1 minus 2, so it would be y to the -1. Okay, so this is our version of it with all the exponents in the denominator, all the variables. And John wants us to write it with all the variables in the numerator. So this is exactly what we've got. X to the -4, y to the 5th, minus x squared, y to the -1. Okay? So sometimes our answer will just jump right into the form John is asking for. Other times, we'll have to use what we know about negative exponents to flip things around to get it to how he wants it. This is a super useful exercise, and I want you to make sure that you understand that if you need to, rewind and go figure that out. Again, because this is super useful. You can pause it right now and copy this if that is helpful to you. But we have one more problem. And it looks like this. John says use distributive property to expand. Write the answer with all the variables in the denominator. So again, my advice to you is don't worry about the form until the very end. Just do distributive, work it out as best you can. Then when you get to the point where you feel like you're done, then reshape it into whatever John wants. Because that's what John gets. Okay, again, there's some negative exponents we could clean up, but let's just leave them. Let's not do any extra work until we're sure we need to do it, and let's just do the distributing and see what happens. All right, I want to go alphabetical here. A is just A. Notice it's A to the first power. I'm not going to write it here, but I just did that to make sure. B is 1. Now remember, B1 plus -1 is going to be b to the 0 power. Dun, 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 dun. If you want, you can write b to the 0 power and then cross it off right away because you know anything to the 0 power is a 1 and we don't need it because we're multiplying all this. I do prefer this to just not writing down anything because then it looks like you forgot. Writing this makes it clear, yeah, I know I don't need that anymore. And then k doesn't have any friends. So sad. Okay, then we're going to subtract. Number goes first. B, k squared, p squared. Okay, and now our denominators. This will be, let's see, k squared p to the -2, and then b, p to the -2. Okay. Now let's see if there's anything we can reduce using the quotient rule before we try to arrange this. So what I notice is, look, there's a k squared and there's a k squared. I can use this as a simple canceling, or I can think of this as the quotient rule, where it's k to the 2 minus 2. But in either case, those guys cancel each other out. Oh, I like it so much. So we're left with this and this. Over here, let's see, here's a pair of b's. Again, we can think of it as 1 minus 1, or we can think of it as, oh, b over b, that's a cancel. But there we go. Now, what about this p? This is quotient rule, so now we subtract them. 2 minus a -2 is 2 plus 2. So this would be I'm going to cross both of those out, and I'm going to write p to the 4th up here. So these are the pieces that are left on this side. So now I'm going to write this, a cleaner version of this. So it's a over p to the minus 2 minus 4 k squared p to the 4th, and it doesn't have any denominator. All right, so there's our answer. Let's see how John wants us to write this again. I forgot, it was a long time ago. All the variables in the denominator. Okay, so we need to move this down, and then we need to move this down and this down. But listen again to what John says, all variables in the denominator. This is not a variable. We need to move this one down too. This is not a variable. That is a number, a fixed number. So that can stay in the numerator. That's tricky. That's what I was talking about a few minutes ago, where I was saying John words these things very carefully. The numbers usually stay up top. So we're going to make this one 1 over. This a is going to have to become a to the minus 1, right? We need to give it the 1 so that it can pop down. P to the minus 2 minus, now the 4 will stay up, and then these guys both need trapezes. K to the minus 2, P to the minus 4. And there's our right answer. Now let me remind you again that of these different ways that we can present the answers that I showed you here, one is not better than the other. There's not one of these that's more right than the others. It's just a question of where you might be going with the calculation. What John tends to do is he mixes this up a lot so that we get practice in moving the pieces into whatever shape he wants. But there isn't a right or wrong to how you arrange. You know, like negative exponents are not always bad. Having variables in the denominator or the numerator, it's neither good nor bad. It doesn't really matter. It's just a question of how you want to do it. All right, guess what? We are done. Let me give you your special Thanksgiving homework assignment. The homework for lesson 40. I want you to do all of the practice. And then, let me just look really fast. Yes, I want you to do from the problem set. I want you to do 15 through 29 odds. Okay, so that'll be about 8 problems, right? 15, 17, 19, 21, 23, 25, 27, 29. 8 problems. Yay! Enjoy your Thanksgiving weekend. Eat lots of turkey. Go hog wild on the desserts. And enjoy a slightly lighter homework load for the week. Okay, I'm done. Goodbye. Thank you.